Hey, and welcome back to DATQVAULT video lectures. This lecture we're going to talk about the effects that different substituents on an aromatic ring happen on the reaction known as electrophilic aromatic substitution. So this lecture actually goes along really well with the lecture on electrophilic aromatic substitution. So if you haven't had a chance to look at that lecture yet, I suggest going and quickly reviewing that lecture or that topic before actually listening to this lecture right here. So right here I have an example of what electrophilic aromatic substitution is, so we can compare it to different substituents that might be on the aromatic ring. So if you remember, electrophilic aromatic substitution, or EAS, the aromatic ring acts as a nucleophile and will come out and will attack some sort of electrophile and kick off a leaving group. The leaving group will then deprotonate the hydrogen on the aromatic ring and restore aromaticity, giving us our substituted product, and also HX as a byproduct. So in the video on electrophilic aromatic substitution, we only used benzene as an example of a nucleophile in the reaction, but of course you're not just going to only want to use benzene in this reaction. You're going to want to use a number of aromatic starting materials that might have different substituents on them, right? So here I have an example of an aromatic ring that has just some arbitrary substituent on it. We'll just label it as R. So depending on what this R group is, we can actually get substitution at a number of different positions on this aromatic ring. We can get substitution on the opposite side of the aromatic ring. This is known as substituting the ring at the para position. We can also substitute this hydrogen on the aromatic ring. This is known as substituting the ring at the meta position. We're talking about the substituent with respect to the electrophile when we're talking about para and meta. And then we can also substitute this hydrogen right here, which is known as the ortho hydrogen to this R group, and we can do an electrophilic substitution at the ortho position. So depending on where we want the substitution to take place on this aromatic ring, we can use a variety of different R groups to direct where we want the electrophile to go, and also depending on what the R group is, we can actually affect the rate at which the reaction actually happens. So I realize that some of you might be wondering right now when I will ever need to use this information if I'm just going to be a dentist. So really, I think this kind of thinking can be really detrimental to your education. So the basic sciences, like organic chemistry, are really foundational for further courses in science. And although you won't be doing any chemical reactions as a dentist, having a basic understanding of the building blocks of science, such as substituent effects and electrophilic aromatic substitution, will allow you to have really a deeper understanding of courses that you might take in the future, like physiology, anatomy, and especially courses like pharmacology. So the further you get into dental school, really, the more connections you're going to be able to make with seemingly once disconnected courses like organic chemistry. So really stick with this stuff, guys. Study hard, and you'll definitely see stuff like this the further on you get into dental school, and it'll help you learn much faster in other courses. So let's continue talking about these substituent effects. One of the groups of substituents that affects electrophilic aromatic substitution are known as electron donating groups. These groups have lone pairs of electrons that help direct the electrophile to substitute at the ortho or para position on the aromatic ring, and these electron donating groups are also activators of the aromatic ring. So it allows the reaction to occur much faster. An example of an electron donating group is this methoxy group. So this molecule right here is known as anisole. This oxygen has two lone pairs of electrons that are able to donate into the aromatic ring to make this aromatic ring A more nucleophilic and B, direct the electrophile to substitute at the ortho position here or the para position here. So actually what's cool about this reaction is when you have a strong activator like this methoxy group, you actually don't even need a strong Lewis acid to even promote this reaction. It'll just go in the presence of Br2. The second group of substituents that affect substitution and rate of reaction are known as electron withdrawing groups. So these groups are meta-directors, and they are also deactivators of the aromatic ring. So they make the reaction go actually much slower than compared to just a benzene molecule. An example of an electron withdrawing group is a nitro group. Nitro groups are, of course, extremely electron withdrawing groups with a strong dipole going towards the nitro group. So if we did this reaction of nitrobenzene in the presence of Br2 and iron tribromide, we would actually get substitution in the meta position instead of the ortho or para positions. And we'll go over why this is later on in this lecture. But first, let's focus on ortho-para directors. So why exactly would anisole, so this methoxy group on this benzene molecule, act as an ortho-para director? And why does substitution not happen in the meta position? So here is the intermediate of an electrophilic aromatic substitution if the aromatic ring were to attack the bromine in the para position. So now we have the bromine substituted in the para position, and that gives us a carbocation at this position of the molecule. We can take this lone pair of electrons from the methoxy group, and through resonance we can form this structure here. So the fact that we have this methoxy group, we can actually form an additional resonance structure of this molecule that can further stabilize it, thus favoring substitution at the para position. This also happens if we substitute the bromine for the hydrogen in the ortho position. So we get the carbocation here in the aromatic ring, and again, through resonance, we can actually donate this lone pair of electrons to get this resonance structure. So we can either get substitution in the para position or the ortho position. It's good to note that between these two positions for substitution, para is actually favored over ortho, because if we brominate in the ortho position, there might be some steric interference between this bromine group and this methoxy group. So between these two, para is favored over ortho, but they're both highly favored over meta. And that's because if we were to try to substitute it in the meta position, there are no resonance structures to actually stabilize the carbocation. Alright, so a lot of common ortho-para directors can be either aromatic groups, alkenes that are conjugated to the aromatic ring are also good ortho-para directors, and also just plain old alkyl groups are also decent ortho-para directors. These groups are not very strongly activating for the aromatic ring because a resonance structure with them creates another carbocation instead of putting a positive charge on a heteroatom such as an oxygen or a nitrogen, which is actually more favored. Which brings us to our next set of common ortho-para directors, are alcohols, ethers, or esters. Again, it's this lone pair of electrons on these oxygen atoms that actually will donate in and create additional resonance structures to stabilize the carbocation. Also, strong ortho-para directors and strong activators are also either amines, primary, secondary, or tertiary amines work for this. And also amides work because, again, we have this lone pair of electrons on this nitrogen that can donate and stabilize that carbocation. Alright, let's talk about meta-directors. So why are electron withdrawing groups good meta-directors We know why they're good deactivators is because they take away electron density from the aromatic ring, so it makes them poor nucleophiles. But why do they prefer to substitute, if they do substitute at all, to the meta position versus the ortho position? Again, this right here is the meta position. So why doesn't it substitute in either this position ortho or this position the para position? So the intermediate, just like I showed you previously for the ortho para directors, if you were substituting the ortho position, the cation would be at this position of the molecule. And because this nitro group is so electron withdrawing and has such a strong dipole, it is going to pull electron density away from an already unstable carbocation. So it makes this molecule even less stable. Again, we have the same thing happening if we were to substitute the bromine in the para position. And that's because this electron withdrawing effect of this nitro group and the fact that it cannot donate any electrons to stabilize this carbocation is going to further deactivate it and further destabilize it. So that makes these two structures heavily disfavored. So here we have substitution of the bromine in the meta position. So these nitro groups are called meta directors because this dipole is not going to affect the charge imbalance on this carbocation quite as much as it would if the charge were on the carbon directly attached to this electron withdrawing group. So even though the structure is more favored versus these two structures, this nitro group is still deactivating this compound, and it's still going to be less reactive than a regular benzene molecule would be. But if this nitrobenzene were to go under electrophilic aromatic substitution, because of this effect that we talked about here, it's going to substitute it in the meta position and not the ortho and para positions. Alright, a lot of common meta directors are, of course, all the carbonyl compounds, so ketones, aldehydes, carboxylic acids, esters, acid chlorides, or any kind of acid halide are going to be good meta directors. That's because they are extremely electron withdrawing, because the negative charge is going to go up on the oxygen, there'll be a positive charge on this carbon, and if our aromatic ring was over here and the positive charge was here, this is going to be a strongly disfavored structure to have this kind of charge imbalance. Other common meta directors and strong deactivators of the aromatic ring are also nitriles, nitro groups, like I showed you guys on the previous example, and also sulfonyl groups. Alright, so we've gone over all the carbonyls and also strong activators, but what about halides? What will they actually do if they were already substituted on an aromatic ring and we try to do electrophilic aromatic substitution? They end up actually being deactivators because, one, they are strongly electron withdrawing, so they're going to deactivate the aromatic ring, but they actually end up being ortho-para directors if electrophilic aromatic substitution was to actually happen. So like I said, they are going to deactivate the ring because there is a strong dipole. This chlorine is very electronegative, so it's going to pull electron density out of the aromatic ring, deactivating the aromatic ring. But you can also take one of the lone pairs on the halogen and donate it down into this bond. And just like all of our activators, such as methoxy groups and alcohols, this sort of resonance is actually going to activate the ring towards being an ortho-para substitution. So let's look at an example. So we have chlorobenzene here, and we're going to do an electrophilic aromatic substitution with nitric acid and sulfuric acid. So this is going to be a nitration of the aromatic ring. The products of this reaction could possibly be para substitution, it could be meta substitution, or it could be ortho substitution. But we're actually going to favor the para and ortho positions because of this donation of the lone pair of electrons from the halogen. So if we were to actually get percentages on this, para would actually be 69% of this overall reaction mixture. Substituting at the ortho position would be around 30%, and substituting at the meta position would only be about 1%. Again, para, just like in the previous ortho meta para directors that we looked at, is going to be favored over ortho because there is some steric hindrance that's happening here between this nitro group and this chlorine. Alright, so let's test our knowledge here that we learned in this lecture on a DAT style question. So here we're asking, what's the major product of the following chemical transformation of this substituted aromatic compound with Br2? So why don't you take a second, try to answer this question, and then we'll answer it together. Alright, so let's go over the answer to this question. If I were to tackle this question, this is how I would do it. Again, the DAT is a computerized exam, so you're not going to be able to actually draw on the test itself. So you're given kind of a whiteboard dry erase thing to work with on this exam, so which is represented by this rectangular box over here. So the first thing that I would do in this question is I would actually draw out the structure so I can start making sketches of what I think are possibilities for the substitution. So we are going to have a nitrile, and we also have a methoxy group on here. So we need to figure out what these groups are. Are they activators, deactivators, meta directors, ortho directors, para directors? So we know that deactivators tend to be meta directors, and we know that activators, such as a methoxy group, tend to be ortho and para directors. So now I want to actually circle the places on this aromatic ring that are going to be most favorable to actually substitute. So let's start with this ortho para director. Here's the para substitution to this methoxy group, and here is one of the ortho positions. We're obviously not going to substitute it at this position because it already has a substituent on it. We know that the meta positions for this nitrile group are going to be favored. So again, here's the meta position, and here's the other meta position to this nitrile. So really we only have two positions on this molecule that are possible for substitution. So I'm going to write out the letters here and start crossing off which ones are not going to be favored. So choices A and B are definitely not going to be favored because they are in the positions on this ring that are not circled. But if we look at answer E, we notice that bromine is substituted in both of the positions that we have here. But if we were to substitute bromine one time and then again, we notice that if we put a bromine on this molecule once, we know that halogens are, again, ortho-para directors. And if we put this here, this position that's also favored is at the meta position. So it's going to be deactivated. So we're not going to get the dibromination product. So that leaves us with answers C and D. Both of these positions is both almost as likely to get substituted, except if we substitute down here in this position, it's closer to the other substituents, creating steric hindrance. So the most favored position for this molecule is going to be the position that's farther away from the other substituents, but also, of course, in an ortho-para position to the methoxy group, which is going to be molecule C. Alright, so this concludes this lecture on substituent effects on electrophilic aromatic substitution. So just to remind you guys that there are practice problems and exams on this topic that you can actually use to further solidify what we've learned in this lecture. So I highly recommend you do that, and then see you back for the next lecture.